The pager goes off at 3:14 in the morning and the graph is a cliff. Check out P99 latency, 40 milliseconds all week, then a vertical wall to 11 seconds. Not a spike that recovers. A step change that stays. Nothing deployed in 6 hours. No traffic surge, requests per second are flat, actually slightly down, because it's 3 in the morning. The database CPU is pinned at 94% and the disk read throughput has gone up by a factor of 200. One query is doing it. A lookup by email address on the users table. The same query that has been in production, untouched, for 2 years. So let's do the autopsy properly, because the answer is not the database got slow. Databases don't get slow. They get asked to do more work, and the amount of work a query does can change by 4 orders of magnitude while the query text stays byte for byte identical. Start with what the engine actually has to do. That query says, find the row where email equals this string. The users table has no index on email. So the engine has exactly one strategy available to it: read every row and check. Row 1, is your email this? No. Row 2? No. All the way down. That's a sequential scan, and its cost is not a constant. It's a function of how big the table is. 2 years ago at launch, users had 8,000 rows. 8,000 rows fits in a few megabytes, which means it fits entirely in the buffer pool, the database's in-memory cache of pages it has recently touched. Scanning 8,000 rows in RAM takes under a millisecond. The query was never fast because it was well written. It was fast because the table was small enough that being wrong about it didn't cost anything. Last night the table crossed a threshold. Not a magic number in the code, the point where the table no longer fits in the buffer pool. Now every scan has to pull pages off disk, and it evicts other things to do it, so the next query misses too, and the one after that. That's the cliff. Not linear degradation. A phase change, because the storage layer underneath you changed which physical device it was reading from. Which is the first thing worth carrying out of this: unindexed queries don't fail loudly when you write them. They fail 18 months later, at scale, at 3 in the morning, in a code path nobody has touched. Now the fix, and the reason it works. An index is a second data structure that stores your columns' values in sorted order, each one paired with a pointer to where the full row physically lives. That's the whole idea. You are trading disk space and write throughput for the ability to do a targeted search instead of an exhaustive one. The reason sorted order matters so much is that sorted order permits binary search. With 8 million unsorted rows you need 8 million comparisons in the worst case. Sorted, you need about 23. Every comparison halves the space you still have to consider. That's the difference between a factor of 2 speedup and a factor of 300,000 speedup, and it is why indexing is the single highest leverage thing in the database toolkit. But almost nobody uses a plain binary tree for this, and understanding why tells you most of what you need to know about real index behavior. A binary tree node holds one value and 2 pointers. Follow a pointer and you jump to some other location, which, if the tree lives on disk, means a separate read. Depth for 8 million rows is about 23 levels, so 23 disk reads. Disks, even fast ones, hate that. The unit a disk hands you is not a byte, it's a page, typically 8 kilobytes. You pay nearly the same cost to read 8 kilobytes as to read 8 bytes. So the B tree does something that looks almost lazy. Instead of one value per node, it puts hundreds per node, as many as fit in a single page. A node with 500 keys has 501 children. That's the fanout, and fanout is what collapses depth. One level addresses 500 rows. 2 levels, 250,000. 3 levels, 125 million. 4 levels, 62 billion. Which means the practical answer to how many disk reads to find one row in a 100 million row table is 3 or 4. And the top levels are so frequently touched that they're permanently resident in memory, so realistically you pay one physical read. That is the entire reason a database can answer a point lookup on a billion row table in under a millisecond. Not clever code. Shallow trees, because the tree was shaped around the physics of the storage device. There's a second property worth naming. B-tree leaf nodes are chained together in sorted order, left to right. So once you've descended to a starting point, you can walk sideways. That single detail is why one index serves equality lookups, range scans, prefix matching on text, and sorted output without a sort step. It's why an index on created_at answers everything from last Tuesday efficiently, and why order by on an indexed column can be free. Now, the part of the autopsy that trips people up. Adding the index doesn't always help, and the engine is allowed to ignore it. Suppose instead of email, the slow query filtered on a status column with two values, active and cancelled, and 95% of rows are active. You add an index. The query gets no faster, or gets slower. The optimizer looked at your index and declined to use it, and it was right. The concept is selectivity. What fraction of the table a predicate eliminates? Email is high selectivity, one value, one row. Status is terrible, one value, most of the table. Using an index means walking the index to collect pointers, then following each pointer to fetch the actual row, and those fetches land in effectively random disk locations. Random reads are dramatically more expensive per row than sequential ones. Past roughly 5 or 10% of a table, doing millions of random fetches is slower than just reading the whole thing in physical order. So the optimizer computes both costs from its statistics in picks. When people say I added an index and nothing happened, this is usually what happened, and the index is now pure cost, disk space plus a write penalty, zero benefit. That write penalty deserves its own moment, because it's the part that gets left out. Every index is a promise the database has to keep on every write. Insert a row into a table with 6 indexes and you're not doing one write, you're doing 7, plus potential page splits when a node fills up and has to be broken in 2. Indexes make reads faster by making writes slower. On a write-heavy table, a pile of speculative just-in-case indexes is a self-inflicted throughput problem. The right number of indexes is the smallest set that covers the queries you actually run. There's an escape hatch for the low selectivity case, though, and it's underused. If 95% of rows are active but your queries only ever hunt for the cancelled ones, you don't need an index over the whole column, you need one over the interesting slice. That's a partial index, an index with a where clause baked into its definition. It indexes the 5% and ignores the rest. Suddenly the predicate is selective, the index is a fraction of the size, and the write penalty only applies to rows that match the condition. The canonical version of this is indexing unprocessed jobs in a queue table, where the millions of completed rows are deadweight you never query. It's also worth knowing that the B tree isn't the only shape available. A hash index stores a hash of the value instead of the value itself, which buys constant time equality lookups, theoretically better than a tree descent. But hashing destroys ordering, so a hash index cannot do range scans, cannot do prefix matching, and cannot supply sorted output. That's why B trees remain the sensible default, slightly worse at the one thing hash indexes are good at, dramatically more useful everywhere else. A specialized structure that only answers one question is usually a worse deal than a general one that answers 5. 2 more ideas and then the resolution. Composite indexes, an index over several columns together, obey a rule that surprises people, the leftmost-prefix rule. An index on last_name, first_name, city is sorted by last name, then within each last name by first name, then by city. That structure can serve a query filtering on last_name alone, or last_name and first_name, or all three. It cannot efficiently serve a query filtering on first_name alone. Think of a phone book sorted by surname. Finding everyone called Ahmed is trivial, finding everyone whose given name is Yusuf means reading the entire book. Column order in a composite index is a design decision, not a formality. And covering indexes. Normally the index gets you a pointer and then you fetch the row for the columns you asked for. But if the index happens to contain every column the query needs, the engine can answer entirely from the index and never touch the table at all. That's an index-only scan, and it's often a several-fold win on top of the indexing itself. It's also why a slightly wider index sometimes beats a narrower one. Back to 3:14 in the morning. The resolution was a single index on email, created without locking writes, because on Postgres you build it concurrently, and dropping a lock on the users table during an incident turns one outage into a worse one. Latency went from 11 seconds to under a millisecond. Sequential scan of 8 million rows became a 3-level descent. But the actual root cause was never the missing index. It was that nobody had a signal for the gap between query is fast and query is scalable. Those are different properties, and load testing against a seed database of a few thousand rows cannot tell them apart. The durable fix was cheap, log slow queries above a threshold, and treat a sequential scan on a growing table as a defect at review time rather than at 3 a.m. So the shape of the thing. An index is sorted redundancy, you spend space and write speed to convert exhaustive search into targeted descent. It's a B tree rather than a binary tree because the disk deals in pages, and high fan-out is what keeps the tree 3 or 4 levels deep instead of 23. And an index only earns its cost when the predicate is selective enough that fetching scattered rows beats reading the table straight through, which is why the optimizer sometimes overrules you and why every index you add is a tax collected on every insert forever. The tool that makes all of this visible is the query plan. On Postgres, explain analyze runs the query and reports what it actually did versus what it predicted. Sequential scan where you expected an index scan means either the index doesn't exist, the predicate isn't selective, or the statistics are stale. A wild gap between estimated and actual row counts almost always means stale statistics, and the optimizer is making decisions from a picture of a table that no longer exists. Which leaves two things worth sitting with. Pick the query in your own system that runs most often, do you know, not assume, whether it uses an index, and have you read its plan? And on your busiest write table, could you name what every index on it is for, or are some of them there because someone added one during an incident and nobody ever took it back out? The uncomfortable truth in this whole autopsy is that the query was never good. It was small. Scale doesn't create bugs like this, it reveals the ones that were always there, on a night when you'd rather be asleep.